Close your eyes for a moment and picture this: a world where the ground beneath your feet isn't solid at all, but a vanishing act in slow motion, where mountains, those symbols of permanence, once crumbled like sandcastles against the tide, and entire oceans disappeared without a trace. This isn't science fiction. This is the story of the Alpine Ocean, a lost world that once sprawled across Europe, its waters teeming with life, its fate sealed by forces beyond imagination. Today, its ghost lingers in the very bones of the Alps, whispering secrets to those who know how to listen. How do you trace the footsteps of an ocean that vanished millions of years ago? Scientists have become detectives of deep time, piecing together clues hidden in the most unexpected places: a fossilized shell trapped high in a mountain peak, a peculiar ripple in ancient rock, a magnetic signature locked in stone. Each clue is a puzzle piece in a drama that unfolded over eons, a collision of continents so powerful it swallowed seas and birthed new landscapes. But this isn't just a tale of the past. The collapse of the Alpine Ocean holds urgent lessons for our future, from how climate shifts can rewrite entire continents to the fragile dance between land and sea. So why does this ancient cataclysm matter to us now? Because Earth's story is never truly over. The same forces that melted mountains and erased oceans still shape our world today: rising temperatures, shifting tectonic plates, the slow but relentless march of geologic time. By unraveling this mystery, we're not just uncovering the past, we're learning to read the language of our planet, to predict its next moves. So join me on a journey back through millions of years, to an era when the Alps were just a dream in the Earth's molten heart, and discover how the echoes of that ancient collapse still ripple beneath our feet. The adventure begins now. Long before the jagged peaks of the Alps pierced the sky, a sprawling blue expanse dominated the landscape: the Alpine Ocean, a lost world born from the fractures of a dying supercontinent. Imagine standing on the shores of this ancient sea 250 million years ago, where the air hummed with the sounds of unseen creatures and the ground trembled with tectonic restlessness. This wasn't just any body of water. It was a geological crucible forged by the breakup of Pangaea, Earth's last great supercontinent. As colossal landmasses tore apart, the crust stretched thin like taffy, creating a gaping wound that soon filled with seawater. But this wasn't a peaceful process. Molten rock surged upward, volcanoes belched ash into the sky, and the ocean floor cracked open like a shattered mirror. The real drama lay beneath the waves, where tectonic plates played a deadly game of tug-of-war. On one side, the African plate lurched northward, while the Eurasian plate stood its ground. Between them, the newborn ocean basin widened, its depths accumulating layers of sediment that would one day become the Alps themselves. Yet even as the Alpine Ocean grew, its fate was already sealed. The same forces that birthed it, the relentless drift of continents, would later conspire to destroy it. Along its edges, subduction zones began to form, where oceanic crust slid grudgingly beneath the continents, disappearing into the Earth's molten mantle. These zones became the ocean's Achilles heel, setting the stage for a collapse that would unfold over millions of years. What's astonishing isn't just the scale of this ancient ocean, but how its birth mirrors processes still shaping our planet today. Off the coast of East Africa, the East African Rift Valley tears at the continent like a zipper, a modern echo of Pangaea's breakup. And beneath the Atlantic, the mid-Atlantic ridge continues to spew lava, widening the ocean by centimeters each year, just as the Alpine Ocean once expanded. These parallels remind us that Earth's story is cyclical. written in the language of moving plates and vanishing seas. The Alpine Ocean may be gone, but its legacy lives on, locked in the rocks beneath our feet and the mountains that now tower where its waves once rolled. The Alpine Ocean at its peak was a world of staggering beauty and biodiversity, a shimmering aquatic paradise where sunlight danced on turquoise waters teeming with life. Picture coral reefs more vibrant than the modern Great Barrier Reef, their limestone skeletons built by ancient organisms called rudists, strange, tube-shaped mollusks that formed massive underwater colonies. These weren't the delicate branching corals we know today, but robust, honeycomb-like structures that created entire ecosystems. Schools of prehistoric fish darted between them, their fossilized scales later found in alpine quarries, while coiled ammonites, distant relatives of squid, drifted like living submarines, their spiral shells evolving into intricate patterns over generations. But the ocean's secrets aren't just locked in fossils. Sediment cores drilled from deep beneath the Alps tell a vivid story of its chemistry and currents. Layers of dark, organic-rich shale reveal periods of abundant plankton blooms, suggesting nutrient-rich upwellings similar to those off Peru's coast today. Thin bands of reddish iron oxide hint at sudden drops in oxygen, like snapshots of ancient dead zones. And then there are the tiny, tooth-like conodont fossils, microscopic remains of eel-like creatures that serve as nature's thermometers. By analyzing their chemical makeup, scientists discovered the Alpine Ocean's surface waters once reached bathtub-warm temperatures, a steamy 30 degrees Celsius in some regions. The shores were just as lively. Fossilized mangrove roots and palm fronds found in Switzerland's Glarus Alps paint a surreal picture, a coastline more reminiscent of the Bahamas than the snow-capped peaks we know today. Crocodilians basked in brackish lagoons while pterosaurs swooped overhead, snapping up fish. Even the ocean's floor tells tales. Ripple marks preserved in sandstone show where powerful tides scoured the seabed, and burrows left by worm-like creatures trace intricate labyrinths in the mud frozen in time. Yet for all its abundance, the Alpine Ocean was living on borrowed time. Deep below, the African plate continued its slow, crushing advance, warping the seafloor into trenches and igniting underwater volcanoes. Sediment layers grow abruptly thicker toward the ocean's southern edge, a silent testament to the growing weight of approaching continents. And in the fossil record, subtle shifts appear. Ammonite species that once thrived for millions of years vanish, replaced by hardier forms adapted to turbulent waters. The Golden Age was ending, not with a bang, but with a creeping unease written in stone. Beneath the serene surface of the Alpine Ocean, a geological time bomb was ticking, one measured not in seconds but in millions of years. The same tectonic forces that had created this vast sea were now conspiring to destroy it, as the African plate crept inexorably northward at about the speed your fingernails grow. That might sound slow, but over geological time, it was a collision course with catastrophe. The key to this destruction lay in something called a subduction zone, a place where one tectonic plate plunges beneath another like a conveyor belt disappearing into the earth. Along the Alpine Ocean's southern edge, dense oceanic crust began sinking beneath the lighter continental crust of Europe, dragging entire swaths of seafloor down into the scorching mantle. This wasn't a clean process. As the plates ground against each other, they created earthquakes that would have dwarfed anything we experience today, each tremor a harbinger of the ocean's impending doom. What's fascinating is how scientists uncovered these ancient subduction zones. They found telltale rocks called blueschists, rare, blue-tinged minerals that only form under extreme pressure deep in subduction trenches. These rocks, now exposed in the Swiss Alps, are like forensic evidence from a crime scene, proving where and how the ocean's crust was swallowed. Even more telling are ophiolite slices of ancient seafloor thrust up onto land like geological trophies, preserving pillow lavas that once erupted underwater. But subduction didn't just erase the ocean, it transformed it. As the plate descended, water trapped in its rocks was squeezed out, lowering the melting point of the mantle above. This spawned violent volcanoes along Europe's edge, their eruptions raining ash over what would one day become the Matterhorn. Meanwhile, the ocean itself began to shrink, its coastlines retreating as if someone had pulled a plug. Marine fossils found in the Dolomites show creatures once thriving in open water suddenly adapted to shallow lagoons, then disappeared entirely as their world vanished beneath them. The cruel irony, this slow-motion destruction sowed the seeds for the Alps' creation. Every bit of ocean crust that vanished was eventually recycled into new land, melted and reborn as the granite bones of future mountains. The Alpine Ocean's fate was sealed not by chance, but by the relentless logic of plate tectonics, a reminder that even Earth's grandest features are temporary players in a much bigger story. The ocean floor of the Alpine Ocean didn't just vanish quietly, it fought back, twisting and contorting into a chaotic underwater battlefield as the continents closed in. Imagine the seafloor crumpling like a rug pushed against a wall, its once smooth plains buckling into jagged peaks that rose thousands of meters from the abyss. These weren't ordinary mountains, they were the precursors to the Alps, born beneath the waves in a slow-motion collision that would one day lift them skyward. Deep trenches split the seabed like scars, swallowing entire sections of crust into the Earth's molten depths. Along their edges, volcanic arcs erupted in fiery defiance, spewing lava that cooled into chains of islands, nature's way of marking the boundary between the diving oceanic plate and the advancing continent. Today, these volcanic remnants can still be found in places like the Adamolo Massif in Italy, where granite plutons tell the story of magma chambers that once fed eruptions under the sea. But the most dramatic changes came from earthquakes, not the brief jolts we experience today, but relentless, grinding quakes that lasted for centuries. Sediment cores from the Alps reveal layers of jumbled rock called turbidites, evidence of underwater landslides triggered by these endless tremors. Picture towering walls of sediment collapsing into the deep, only to be swallowed by subduction zones and recycled into new rock. What's extraordinary is how these submerged mountains mirrored the future Alps. The same folds and faults that shaped the underwater ranges would later be lifted, dried, and exposed as the iconic peaks we know today. Even the composition of the rocks matched. Ophiolites, those slices of ancient seafloor, now perch atop Mont Blanc and the Matterhorn, proving their oceanic origins. The ocean's death throes weren't just destructive, they were creative. Every trench, every volcanic island, every earthquake was laying the groundwork for a new world. The Alps didn't rise from nothing. They were forged in the chaos of a disappearing ocean, their birth as violent as it was inevitable. The first tremors of the Alpine Ocean's collapse would have been imperceptible to any creature swimming its waters. A slight shudder deep below, a barely measurable shift in the seafloor's tilt. But for geologists reading the rocks millions of years later, these were the opening lines of a geological obituary. As subduction zones along the ocean's edges grew more voracious, they began consuming the seafloor at an alarming rate, dragging entire sections of crust down into the mantle like a conveyor belt to the underworld. The ocean's once stable basin started to warp, its floor buckling into deep troughs where sediment piled up in frantic, chaotic layers, nature's frantic attempt to fill the void. One of the clearest signals of this collapse comes from paleomagnetism, the ancient magnetic signatures locked into volcanic rocks on the seafloor. As magma erupted along mid-ocean ridges, tiny magnetic minerals within it aligned with Earth's magnetic field like compass needles, freezing that orientation as the rock cooled. By mapping these orientations across the Alps, scientists discovered bizarre twists and folds in the magnetic record, proof that the seafloor had been stretched, torn, and contorted during subduction. Some rocks even showed magnetic reversals stacked haphazardly, a sure sign the crust had been mangled beyond recognition. Meanwhile, the ocean's coastlines began retreating at a geological sprint. Fossilized shorelines now found high in the Austrian Alps tell a story of rapidly shallowing waters, where coral reefs that once thrived in deep blue seas suddenly found themselves suffocating in muddy shallows. Layers of gypsum and salt deposits minerals that only form when seawater evaporates suggest entire bays were cut off from the main ocean, left to bake under the sun like abandoned swimming pools. Beneath it all, the real drama unfolded in the magma chambers. As the subducting plate dove deeper, it carried water-rich minerals that lowered the melting point of the overlying mantle. This spawned vast reservoirs of molten rock that bubbled upward, some erupting as undersea volcanoes, others cooling slowly into granite plutons. Today, these plutons form the crystalline hearts of mountains like the Mont Blanc, massive literal monuments to the ocean's destruction. Perhaps most haunting are the mélange zones, chaotic jumbles of rock where slices of ocean crust, continental fragments, and even mantle material were mashed together like geological Frankenstein's monsters. These zones, now exposed in places like the Glarus Alps in Switzerland, show rock types that should never coexist: serpentinite from the mantle pressed against limestone from a coral reef, all smeared into a single chaotic layer. Walking through these formations is like stepping into the scene of a tectonic crime, where the very fabric of the ocean was shredded beyond repair. Yet even in collapse, the Alpine Ocean shaped its own legacy. Every swallowed piece of crust would eventually resurface, melted and reborn as the building blocks of the Alps. The same forces that destroyed this ancient sea were already laying the groundwork for its most enduring monument, proof that in geology, as in life, endings are often just beginnings in disguise. The sedimentary layers left by the Alpine Ocean are like a geological diary, each page crisply preserved despite being written millions of years ago. To read them, scientists don't just look at the rocks, they decode the stories hidden in their textures, compositions, and even the slightest chemical variations. Take turbidites, for example, thick, gritty deposits that formed when underwater avalanches raced down collapsing continental slopes. These chaotic layers, now found in places like the Fleisch zone of the Alps, are nature's snapshots of catastrophe. Each coarse-grained base grading into finer silt tells of a single violent event, perhaps an earthquake shaking loose sediment that tumbled into the abyss, only to settle in distinct pulses. Stacked like pages in a book, they reveal how frequently these disasters struck as the ocean's margins grew unstable. But not all sediment speaks of violence. Delicate limestone beds rich in microscopic plankton fossils like coccolithophores whisper of quieter interludes. These tiny, disc-shaped algae thrived in sunlit surface waters, their calcium-rich shells raining down in steady drifts after death. By analyzing their chemistry, researchers can reconstruct sea temperatures, acidity, even seasonal blooms, like reading a prehistoric weather report. In some layers, these fossils abruptly vanish, replaced by dark, organic, rich shale, a silent testament to sudden oxygen depletion that suffocated marine life. Then there are the evaporites, crisp layers of gypsum and halite that form when seawater evaporates entirely. Found in spots like the Swiss Mollusk Basin, they're the ocean's last gasp, marking shallow lagoons cut off from the main body as the sea retreated. Picture a bathtub with the plug pulled, leaving crusty salt rings behind. These minerals are more than just relics, they're stopwatches. By measuring their thickness, geologists estimate how fast the ocean shrank, sometimes at rates of several centimeters per year, a blistering pace by geological standards. Perhaps most haunting are the trace fossils, not the remains of creatures, but their activities. Winding burrows in sandstone show where worms tunneled through seabed mud, their shapes growing shallower and more frantic in younger layers as oxygen levels dropped. Even the ripple marks frozen in stone have tales to tell. Symmetrical wave ripples give way to asymmetrical current ripples, proof that gentle tides were replaced by fierce, one-directional flows as the ocean narrowed into a seaway. What emerges from these layers isn't just a timeline of destruction, but a paradox. As the Alpine Ocean died, it became a sediment trap of unparalleled richness. Rivers from the converging continents dumped sand and mud into its shrinking basin, piling up layers so thick they later helped buoy the Alps upward during their rise. The very process that erased the ocean also created the raw material for its successor. In the end, these sedimentary secrets don't just chronicle an ending, they foreshadow a beginning written in stone. The death throes of the Alpine Ocean weren't silent. They were announced with a roar of fire and ash as the vanishing sea unleashed one last act of geological fury. Imagine standing on what was once a tranquil coastline, only to watch the horizon explode in a curtain of flame as volcanoes erupted along the collapsing ocean's edges. These weren't isolated events, but a chain reaction of devastation and rebirth, where every cubic kilometer of swallowed seawater triggered new explosions deep within the earth. As the oceanic plate plunged into the mantle, it carried with it something unexpected: water. Not just droplets, but entire oceans worth locked in mineral structures within the rock. When this water met the scorching heat of the mantle, it did something extraordinary. It lowered the melting point of the surrounding rock, creating vast chambers of magma that bubbled upward like a boiling pot with the lid left on. The result, volcanic arcs that would make Mount St. Helens look tame. In the Dolomites, towering peaks like the Marmolada bear witness to this violence. Their jagged spires actually fossilized magma chambers that once fed eruptions fiercer than anything seen in recorded history. The eruptions themselves were catastrophic. Ash clouds would have blotted out the sun for months, their particles found today as thin white layers in alpine rock formations, geological bookmarks marking moments of global darkness. But the real climate impact came from the gases. Sulfur dioxide injected into the stratosphere reacted to form sulfuric acid aerosols, reflecting sunlight back into space and triggering volcanic winters. Fossilized leaves from this period show stunted growth and bizarre mutations, evidence of ecosystems struggling under acid rain and dimmed skies. Yet amidst this chaos, creation thrived. The same volcanic activity that choked the atmosphere also fertilized the land. Rich layers of volcanic soil became nurseries for new forests, their nutrients carried by rivers to rejuvenate floodplains. And the magma that didn't erupt, it cooled slowly underground, crystallizing into the granite cores of future alpine peaks. The Matterhorn's iconic pyramid, for instance, owes its existence to a massive pluton that formed during this fiery transition, proof that destruction and creation are two sides of the same coin in geology. The most fascinating remnants of this era aren't the obvious volcanoes, but their hidden plumbing. In the Adamallo Massif, geologists have mapped a fossilized magma chamber over 15 kilometers thick, a frozen snapshot of the underground inferno that once raged beneath the dying ocean. The chamber's intricate crystal layers tell a story of repeated filling and emptying, like a geological bellows feeding eruption after eruption. Some crystals even contain microscopic bubbles of ancient magma, time capsules preserving the exact chemical cocktail that fueled these explosions. What's often overlooked is how these volcanic events sculpted the early Alps. Pyroclastic flows, superheated avalanches of gas and rock, scoured valleys that would later guide glaciers during ice ages. Lava flows formed plateaus that became the foundation for iconic peaks. Even the mineral wealth of the region, gold, copper, and the famous Lepontine garnets were concentrated by these hydrothermal systems, their veins tracing the paths of ancient steam vents. The legacy of this volcanic fury lingers today in unexpected ways. The same tectonic forces that destroyed the Alpine Ocean still occasionally stir, as evidenced by rare but measurable earthquakes beneath the Po Valley. Thermal springs in places like Bormio bubble with waters heated by depths where magma may still lurk. And in the rocks themselves, the story continues to unfold. Every crystal, every ash layer, every twisted lava flow, adding another sentence to the epic tale of how fire and water together forged the Alps. The disappearance of the Alpine Ocean didn't leave an empty stage. It left a battlefield of crumpled rock, molten magma, and unimaginable pressure, all waiting to be sculpted into something new. Picture this: where turquoise waters once stretched, a jagged skyline now began to emerge, piece by piece, as if the Earth itself was pushing upward to fill the void. The birth of the Alps wasn't a single dramatic event, but a slow-motion ballet of collision and compression, where the wreckage of the ancient sea became the raw material for Europe's most iconic peaks. At the heart of this transformation was a process called Continental Collision. With the ocean's protective buffer gone, Africa and Europe finally met in a grinding embrace, their continental crusts too buoyant to subduct like the oceanic plate before them. Instead, the rocks did what stiff bread dough does when pressed. They folded, fractured, and piled upward in chaotic layers. The evidence is everywhere in the Alps today. In the Swiss town of Glarus, you can literally walk across a single rock layer that's been folded into a perfect U-shape, a frozen moment of tectonic stress so extreme it bent solid stone like taffy. But folding was just the beginning. As pressure mounted, entire slabs of rock began sliding over one another along massive faults, stacking like shuffled decks of cards. The famous Matterhorn tells this story in its very structure. Its base is ancient African continental rock, while its summit consists of sedimentary layers from the Alpine Ocean, all thrust skyward in a geological heist. This stacking explains why the Alps contain such bizarre rock sequences, where deep-sea sediments perch precariously atop granite that once lay 20 kilometers below ground. The speed of this uplift would have been breathtaking if anyone had been there to witness it. While mountains seem eternal to us, the Alps rose at a blistering pace by geological standards, up to 5 millimeters per year during peak growth. That might not sound like much, but over 1 million years, it adds up to 5,000 meters. Imagine watching the Eiger grow from a hill to a monster in the time it takes for a single species of hominid to evolve. What's often overlooked is how erosion shaped the Alps even as they rose. Rivers like the Rhine and Rhone carved deep valleys that relieved pressure, allowing the mountains to rise higher, a feedback loop where destruction enabled creation. Glaciers later sculpted the iconic horns and cirques we admire today, but the underlying architecture was forged by those early tectonic forces, the most poetic part. The Alps are still growing. Precision GPS measurements show parts of the range rising by 1 to 2 millimeters annually, outpacing erosion in some areas. Every earthquake in the region, like the 2009 L'Aquila tremor, is a reminder that the continental collision continues just as it has for 30 million years. The Alpine Ocean may be gone, but its final act, the rise of these magnificent peaks, is still being written 1 millimeter at a time. High in the thin air of the Swiss Alps, where climbers gasp for breath and glaciers cling to steep slopes, there's a secret hidden in plain sight: fossilized seashells embedded in the rock. These aren't just random relics, they're time capsules from the Alpine Ocean, creatures that once thrived in warm waters, now frozen in stone thousands of meters above sea level. Among the most striking are the ammonites, their spiral shells so perfectly preserved you can still trace the intricate sutures where their chambers met. Some measure over a meter wide, giants that drifted through ancient currents like living submarines. But it's not just their size that fascinates scientists, it's their final moments. Many of these fossils are found in twisted, contorted positions, their shells crushed or folded as if caught in a violent underwater landslide. These silent screams in stone tell us the ocean's collapse wasn't a gentle fade, it was a chaotic upheaval that buried entire ecosystems alive. Dig deeper and the fossil record reveals even stranger survivors. Take the tiny, coin-sized foraminifera, single-celled organisms that built elaborate calcium carbonate shells. These microscopic timekeepers are found by the thousands in alpine limestone, each species acting like a biological fingerprint for specific ocean conditions. Some thrived only in warm, shallow waters. Others preferred the cold, dark depths. By mapping their distribution, researchers can reconstruct the Alpine Ocean's temperature gradients with surprising precision, like reading a 200-million-year-old weather map. Even more remarkable are the fish fossils from Monte San Giorgio on the Swiss-Italian border, where entire schools were buried mid-swim, their delicate skeletons preserved in stunning detail. Some species show bizarre adaptations, like elongated snouts for probing crevices or flattened bodies for hugging the seafloor, hints of an ecosystem scrambling to adapt as its world shrank. Then there are the real oddballs, creatures that defy modern comparisons. The ceratite ammonites, for instance, evolved shells with fractal-like patterns unlike anything alive today, possibly a response to changing water chemistry. Or the thalatosaurs, marine reptiles with needle-thin teeth perfect for snagging squid-like creatures in the twilight zone. Their fossils, found in the Dolomites, often show stomach contents preserved, fish scales, shell fragments, even the ink sacs of ancient cephalopods. These are snapshots of the ocean's food web, frozen at the moment of burial, but perhaps the most poignant clues come from the fossilized reefs. In the Dachstein limestone of Austria, you can walk across what was once a thriving coral ecosystem, now a sun-bleached plateau at 2,000 meters elevation. The corals themselves tell a story of stress. Their growth bands, much like tree rings, show increasingly erratic patterns as the ocean shallowed. Some colonies exhibit dwarfing, where successive generations grew smaller and misshapen, struggling in murky, sediment-choked waters. Others switched from symbiotic algae to filter feeding, a desperate survival tactic seen in modern reefs under duress. What makes these fossils so extraordinary isn't just their age or altitude, it's how they capture an entire world in transition. They show us life's resilience in the face of catastrophe, but also its limits. As the Alpine Ocean vanished, some species migrated, some evolved, and some simply couldn't keep pace. Their remains, lifted skyward by the rising Alps, are more than scientific curiosities. They're memorials to an ecosystem that thrived, fought, and ultimately vanished, leaving behind stories written in bone and stone. The disappearance of the Alpine Ocean sent shockwaves through Earth's climate system, triggering changes that rippled across the planet for millions of years. Picture this: as the ocean basin closed like a giant zipper, it didn't just rearrange continents, it rewired the entire planetary circulation system. The most dramatic shift came in ocean currents. Before the collapse, warm equatorial waters could flow freely between the Tethys Sea and the global ocean, distributing heat like a massive planetary thermostat. But as the Alpine Ocean vanished, these currents were rerouted, creating new patterns that still influence Europe's climate today. Deep-sea sediment cores tell the story. Layers of microscopic fossils show abrupt changes in temperature-sensitive species, marking when warm water plankton suddenly gave way to cold-adapted forms. The real climate bombshell came from the newly exposed land. As the Alps rose where water once stood, their fresh, light-colored rock surfaces reflected sunlight back into space, a phenomenon called the albedo effect. Computer models suggest this may have cooled global temperatures by as much as 2 degrees Celsius over millennia, enough to nudge the planet toward ice age conditions. Evidence comes from Greenland's ice cores, where trapped air bubbles from this period show a noticeable dip in greenhouse gases. Meanwhile, the growing mountain range acted like a giant barrier to atmospheric circulation, splitting jet streams and creating rain shadows that turned vast regions into deserts. The Sahara's formation owes a small but measurable debt to this tectonic upheaval. Volcanic activity during the collapse added another layer of climate chaos. The same eruptions that built the Alps pumped staggering amounts of sulfur dioxide into the stratosphere, where it formed aerosols that blocked sunlight for decades at a time. Fossilized leaves from this era show telltale signs of stress-stunted growth, thickened cuticles, and abnormal pores, all adaptations to dimmer, cooler conditions. But there's a twist. Over longer timescales, the weathering of fresh volcanic rock consumed atmospheric carbon dioxide, gradually cooling the planet even further. This balancing act between short-term warming and long-term cooling offers a fascinating parallel to today's climate debates. Perhaps the most sobering lesson lies in the pace of change. While the Alpine Ocean's collapse unfolded over millions of years, its climate impacts came much faster, some within just a few thousand years. Sediment layers in the Mediterranean show sudden shifts from deep water deposits to shallow lagoons, proof that sea levels could drop dramatically as water was locked up in growing ice sheets. These aren't just academic observations, they're warnings. Today, as human activity alters climate systems at unprecedented speeds, the Alpine Ocean story reminds us that once certain thresholds are crossed, Earth systems can respond with surprising speed and violence. The rocks don't lie. They show us that climate change isn't just about warmer temperatures, but about entire worlds rearranged beyond recognition. The hunt for the Alpine Ocean's ghost has entered a revolutionary new era, where scientists wield tools straight out of science fiction to map a world that vanished millions of years ago. Imagine satellites orbiting 400 miles above Earth, their lasers measuring alpine peaks down to the millimeter, not to study the mountains themselves, but to detect subtle warping in Earth's crust that reveals where ancient oceanic plates still lurk beneath. These gravity-sensing satellites, like Europe's GOES mission, map density variations so precisely they can pinpoint slabs of the Alpine Ocean's floor still wedged deep underground, their cold, dense rock creating minute gravitational shadows. But the real breakthroughs happen far below the satellite, in laboratories where geochemists zap tiny mineral grains with lasers smaller than a human hair. By vaporizing specks of zircon from alpine rocks, they can extract uranium-lead ratios that serve as atomic stopwatches, dating the ocean's subduction down to plus or minus 500,000 years, a blink in geological time. Other researchers use synchrotron particle accelerators to analyze fossilized marine microbes at nanometer scale, reading their chemical composition like a prehistoric recipe book for ocean temperatures and acidity levels. Then there's the daring work of deep drilling projects like the Alpine Continental Deep Drilling Program, where teams bored over 5 kilometers into the Swiss Alps to pull up cores of rock that hadn't seen sunlight since they were seafloor mud. These cores are time machines, their magnetic minerals still aligned with Earth's ancient magnetic field. their fluid inclusions trapping droplets of Jurassic seawater. One drill site even hit a pocket of methane that turned out to be the decomposed remains of 200-million-year-old plankton, its carbon isotopes revealing details about the ocean's food web moments before disaster struck. Perhaps most astonishing are the seismic surveys that work like planetary CT scans. By detonating small explosions or using vibrating trucks to send shockwaves through the Alps, geophysicists record how the waves bounce off hidden structures. The resulting 3D images show ghostly outlines of subducted plates curling like paper in a furnace, with some sections diving nearly 700 kilometers beneath Europe, twice the depth of the Grand Canyon is tall. Yet for all this technology, some clues still require old-fashioned fieldwork. In the Italian Apennines, paleomagnetists crawl across outcrops with handheld sensors, mapping how sections of ocean floor rotated during collision like pieces of a jigsaw puzzle twisted mid-assembly. Others hike remote valleys with gamma-ray spectrometers, tracing radioactive elements in rocks that act as natural fingerprints for different slices of the vanished ocean. The ultimate goal isn't just to reconstruct the Alpine Ocean, but to understand the rules governing all such vanished seas. That's why researchers feed their data into supercomputers running advanced plate tectonic models, digital crystal balls that can simulate millions of years of continental drift in hours. These models don't just replay the past, they've predicted the discovery of previously unknown microcontinents buried in the Alps, later confirmed by drilling. What's emerging is a revelation: the Alpine Ocean wasn't a simple basin, but a complex archipelago with submerged plateaus and volcanic island chains that influenced its demise. Every technological leap peels back another layer of this ancient mystery, proving that even the most vanished worlds leave echoes for those who know how to listen. The story of the Alpine Ocean's collapse might seem set in stone literally, but scratch beneath the surface, and you'll find a scientific battleground where geologists clash over fundamental questions. One fiery debate centers on subduction rates. Just how fast did the ocean floor vanish into Earth's mantle? Traditional models suggest a steady, plodding process, but recent studies of alpine rock sequences reveal chaotic pulses where subduction accelerated tenfold for brief periods. Some researchers argue these spurts were triggered by slab pull, when dense sections of oceanic plate broke off and plummeted downward like anchors, yanking the rest of the plate behind them. Others point to strange mineral veins in the Alps' eclogite rocks, which suggest fluids lubricated the subduction zone, allowing plates to slip faster. The implications are huge. If subduction wasn't uniform, it could rewrite our understanding of how quickly oceans can vanish, and how abruptly mountains rise in their place. Then there's the mystery of mantle plumes, blobs of superheated rock rising from deep within Earth. A vocal faction insists thermal upwellings beneath the Alpine Ocean weakened the overlying crust, making it easier for subduction to begin. Evidence comes from unusual volcanic rocks in the Dolomites, rich in elements like niobium that typically form in plume-influenced settings. Critics counter that these rocks could just as easily stem from shallow melting during continental collision. The debate isn't academic. If plumes played a role, it means external forces, not just plate tectonics, orchestrated the ocean's demise, the biggest unresolved puzzle. The ocean's missing sutures. When oceans close, their edges typically leave crisp scars called suture zones where continents weld together. The Alps, oddly, have multiple sutures jumbled like a shuffled deck. Some sections show African crust welded to European crust, while others contain slivers of oceanic rock caught in between. One radical theory suggests microcontinents, now buried beneath the Po Valley, acted like bumper cars during collision, fragmenting the ocean's remnants beyond recognition. Others propose the sutures were smeared out by later mountain building, leaving a geological palimpsest that resists decoding. Even the timing sparks disputes. Radiometric dating of alpine minerals produces age clusters that some interpret as proof of 3 distinct collapse phases, while others see a continuous process with periodic pulses. The controversy extends to the ocean's depth. Fossils of deep-sea creatures appear alongside shallow water deposits in the same rock layers, suggesting sections of the seafloor were uplifted even as the ocean existed. What keeps these debates alive is the human element. Science advances not by consensus, but through friction, the clashing of ideas that eventually strikes sparks of truth. Every unanswered question about the Alpine Ocean isn't a gap in knowledge, but an invitation to dig deeper, to question assumptions, and to listen to what the rocks are still trying to tell us. The towering peaks of the Alps are more than just scenic backdrops. They're silent architects of human destiny, their very existence a direct result of the Alpine Ocean's ancient collapse. Consider the Brenner Pass, a natural corridor through the mountains that's been a vital trade route since the Bronze Age. This deep valley wasn't carved by chance. It follows the weak zone where African and European continental plates welded together, a seam in the Earth's crust exploited first by migrating animals, then by Celtic traders, and eventually by Roman engineers who paved it into the Amber Road. The marble used to build the Pantheon, it traveled this very route from the Alps' southern slopes, where the same tectonic forces that destroyed the ocean exposed pristine limestone deposits. Fast forward to the Middle Ages, and the Alps became Europe's ultimate natural fortress. The Swiss Confederacy's legendary independence was born in mountain valleys so steep they rendered cavalry useless, valleys shaped by glaciers that, in turn, owed their existence to the alpine uplift's climate effects. Even warfare adapted to the terrain. The Hohentuil volcano in Germany, part of the Alpine Collision's volcanic fringe, became an impregnable castle where medieval armies hunkered behind walls of hardened lava. Meanwhile, alpine minerals fueled entire industries. The Tyrolean silver mines that financed the Habsburg Empire tapped into veins formed when hydrothermal fluids circulated through faults created during the mountain building process. Tourism, the Alps' modern lifeblood, also traces its roots to geology. The very concept of mountain appreciation arose when early geologists like Horace Benedict de Saussure began studying these peaks only to realize their layers told an even grander story. Today's ski resorts in Chamonix or St. Moritz owe their powdery slopes to the same uplift that created rain shadows and snowfall patterns unique to the region. Even the famous thermal baths of Baden-Baden bubble with waters heated by residual geothermal activity from the Continental Collision. Perhaps the most profound human connection lies in culture. The alpine landscape has inspired everything from Heidi's pastoral tales to the eerie mountain symbolism in German Romanticism. The Matterhorn's distinct pyramid shape, a direct result of alternating hard and soft rock layers folded during uplift, became so iconic it influenced everything from Toblerone's packaging to modernist architecture. Local dialects still preserve geological history in place names like Dolomites, derived from the French geologist Déodat Gratet de Dolomieu, who first studied these calcium-rich mountains formed from ancient coral reefs. Nowhere is the past's presence more striking than in alpine agriculture. Traditional cheesemaking in Gruyères relies on summer pastures that exist only because glacial erosion carved high-altitude bowls into the mountainsides. The famous terraced vineyards of the Valtellina cling to south-facing slopes where sunlight bounces off lake-polished rocks that were once sediment at the bottom of the Alpine Ocean. Even the region's notorious avalanches, which claim lives annually, are reminders that the mountains are still rising, still shifting, still writing new chapters in a story that began with an ocean's disappearance. The ultimate irony, the same forces that made the Alps nearly impassable also forced humans to innovate. The Gotthard Tunnel, the world's longest railway tunnel, exists because engineers had to bypass the St. Gotthard Massif, a block of granite thrust upward during the collision. Modern seismic monitoring in the region doesn't just protect towns from earthquakes. It provides real-time data on how the African plate is still pushing north at 2 centimeters per year. Every aspect of life here, from wine vintages influenced by mountain minerals to avalanche barriers designed using fossilized landslide patterns, whispers the same truth: geology isn't just about the past. It's the unseen hand shaping our present and the silent force guiding our future. The collapse of the Alpine Ocean isn't just a relic of deep time. It's a mirror reflecting our planet's most pressing environmental challenges today. When we examine how this ancient sea vanished, the parallels to modern climate change become impossible to ignore. Take ocean acidification. Sediment layers from the Alpine Ocean's final millennia show a dramatic drop in pH, coinciding with mass die-offs of shell-building organisms. Sound familiar? Today, rising carbon dioxide levels are causing similar acidity spikes, threatening coral reefs and marine life worldwide. The difference? Those ancient changes unfolded over thousands of years. We're replicating them in decades. Then there's the lesson of feedback loops. As the Alpine Ocean shrank, its reduced surface area led to less water evaporation, which meant fewer clouds and even hotter regional temperatures, a self-reinforcing cycle. Modern climate models reveal identical mechanisms at work. Melting Arctic sea ice exposes darker ocean water that absorbs more heat, accelerating further melting. The rocks tell us these loops, once started, are hard to stop. Perhaps the most sobering insight comes from the Alpine Ocean's sediment archives. Thin bands of black shale mark periods where oxygen vanished from deep waters, creating dead zones that smothered marine life. These anoxic events were triggered by nutrient runoff from eroding mountains, a prehistoric version of today's agricultural fertilizer pollution, fueling dead zones like the one in the Gulf of Mexico. The scale differs, but the chemistry is identical. But it's not all dire warnings. The Alpine Ocean story also offers blueprints for resilience. Fossil records show certain species, like deep-sea microbes and flexible plankton, adapted to shifting conditions by altering their metabolism or migrating. Modern conservation efforts are applying these lessons, creating marine corridors to help species escape warming waters. Even the Alps themselves demonstrate nature's restorative power. The same forces that destroyed an ocean birthed an ecosystem supporting thousands of species today. The ultimate takeaway: Earth systems have thresholds. The Alpine Ocean crossed one when subduction rates hit a tipping point, triggering irreversible collapse. Climate scientists now warn we're approaching similar thresholds, from thawing permafrost to collapsing ice sheets, but with one crucial advantage: we can read the rocks. Those layers of folded sediment and fossilized struggles aren't just history. They're a roadmap written in stone, showing us where the cliff's edge lies and how to steer clear. High in the thin air of the Swiss Alps, where the wind howls like a restless spirit, a team of geologists chips away at a rock face with hammers that look more like medieval tools than scientific instruments. This isn't just fieldwork, it's a treasure hunt where the prizes are fragments of a vanished ocean, hidden in plain sight for millions of years. Picture the scene: snow-capped peaks towering above, crampons biting into icy slopes, and fingers numb from cold as they pry loose a slab of limestone flecked with tiny ammonite fossils. These scientists aren't just reading Earth's history, they're touching it, one rock at a time. field geology in the Alps is equal parts endurance sport and detective work. Before dawn, teams load packs with gear that would make a mountaineer think twice: rock hammers, chisels, GPS units, and sample bags. Then trek for hours to remote outcrops accessible only by scrambling over scree fields or rappelling down cliffs. The real challenge isn't just reaching these sites, but decoding them. A single square meter of rock might hold the key to unraveling an entire chapter of the Alpine Ocean's demise. Take the famous Lochsatan limestone near Glarus, Switzerland. To the untrained eye, it's just grey rock, but to a geologist, its twisted layers tell of underwater landslides that cascaded down collapsing continental slopes, burying creatures alive in moments of tectonic violence. The tools of the trade have evolved since the days of leather-bound field notebooks. Today, drones buzz overhead, capturing 3D models of cliff faces where human climbers can't safely go. Handheld X-ray fluorescers zap rocks to instantly reveal their chemical makeup, while rugged tablets loaded with mapping software overlay ancient shorelines onto modern topography. But some techniques remain gloriously low-tech. Geologists still lick rocks to distinguish fine-grained mudstone. It sticks to your tongue from siltstone it doesn't, a trick as old as the profession itself. Caves become time capsules in this search. In the Hurlock Cave system, researchers wade through subterranean rivers to study stalactites that grew from mineral-rich waters percolating through limestone that was once the floor of the Alpine Ocean. By analyzing isotopes in these formations, they've reconstructed rainfall patterns from the ocean's final millennia, revealing climate swings that accelerated its collapse. Then there are the accidental discoveries. A hiker once stumbled upon a peculiar greenish rock in the Dolomites that turned out to be a chunk of oceanic crust thrust upward during collision, its olivine crystals still shimmering like frozen droplets of the mantle. Another team, while mapping near Zermatt, found a layer of rock crammed with fossilized shrimp creatures that thrived in hydrothermal vents along the dying ocean's floor, their delicate legs preserved in eerie detail. The work isn't without danger. Loose rockfalls, sudden storms, and altitude sickness are constant threats. One researcher recalls a close call when an entire outcrop of brittle shale gave way beneath his boots, sending him sliding toward a cliff edge until his rope snapped taut. Yet these risks pale next to the thrill of discovery, like the moment a student split open a nondescript boulder to reveal a perfectly preserved fish fossil, its scales glinting in the alpine sun as if it had died yesterday, not 200 million years ago. What keeps these scientists coming back isn't just the allure of discovery, but the visceral connection to deep time. Standing on a ridge where the Alpine Ocean's waves once crashed, holding a rock that last felt sunlight when dinosaurs roamed, they're not just studying history, they're stepping into it. Every hammer strike, every measured layer, every bagged sample is a message in a bottle from a world we can only reconstruct one painstaking clue at a time. Some of the most astonishing storytellers from the Alpine Ocean's demise aren't fossils or sediment layers. They're rocks so extraordinary they defy ordinary geology. Take ophiolites, for instance. These bizarre formations are nothing less than slices of ancient ocean floor thrust up onto dry land, a geological magic trick where the deepest secrets of the abyss sit exposed on mountain slopes. In the Swiss Alps near Zermatt, hikers can literally walk across what was once the Alpine Ocean's crust, stepping on pillow basalt's lava formations that cooled underwater into bulbous shapes resembling giant stone pillows. These rocks are more than just curiosities. They're snapshots of the seafloor's final moments. The rusty red hue of their iron-rich minerals, that's the chemical signature of seawater reacting with molten rock. a process frozen in time when these lavas were abruptly uplifted during the ocean's death throes. Then there are blueschists, the rarest and most revealing of all. These striking blue stones get their color from a mineral called glaucophane, which forms only under extreme pressure, the kind found deep in subduction zones where tectonic plates collide. Picture this: a chunk of oceanic crust gets dragged dozens of kilometers underground, squeezed under pressures equivalent to 3,000 elephants standing on a single dinner plate, then somehow rockets back to the surface. That's the journey these rocks endured, and their very existence is a smoking gun proving the Alpine Ocean's crust was forced into the mantle. Found in places like the Sesia Valley in Italy, blueschists often contain tiny diamonds forged during their subterranean ordeal, microscopic proof of the unimaginable forces that destroyed the ocean. But why are these rocks so vanishingly rare? Most oceanic crust gets recycled completely in the mantle, melted beyond recognition. The ophiolites and blueschists we see today are the lucky survivors, scraped off during collision like frosting between two layers of cake. Their value to science is immeasurable. By analyzing their mineral structures with electron microscopes, researchers have reconstructed pressure-temperature paths, essentially GPS tracks, showing exactly how deep each rock plunged before resurfacing. Some blueschists record temperatures over 500 degrees Celsius, while others bear microscopic cracks from sudden pressure releases, like champagne corks popping under geologic stress. The real magic happens when you compare these rocks across the Alps. In the Western Alps, ophiolites are relatively intact, suggesting gentler uplift. But head east to the Tauern window in Austria, and you'll find ocean crust rocks mangled into swirls and folds, evidence of a violent, grinding collision. This patchwork tells us the ocean didn't die all at once, but in fits and starts, with some areas suffering more brutal fates than others. Even more astonishing are the metamorphic soles, thin strips of rock welded to ophiolites that record the exact moment subduction began. Their mineral clocks indicate temperatures spiking within a mere million years, geologic lightning speed. What makes these stones truly priceless are the secrets they've already revealed, and those they still hold. Recently, a team drilling into an ophiolite in Cyprus, a cousin to alpine formations, discovered microbes thriving in fractures 2 kilometers down, feeding on minerals formed during the rock's submarine origins. Could similar life have existed in the Alpine Ocean's crust? It's questions like these that transform cold, hard stone into the most thrilling history books imaginable, written not in ink, but in fire, pressure, and time. The Alps didn't just rise, they were immediately under siege. Even as tectonic forces heaved these mountains skyward, erosion launched a counterattack, carving, grinding, and dismantling the peaks grain by grain. This wasn't destruction but transformation, a relentless recycling of the Alpine Ocean's remains, scattering its fragments across continents. Picture meltwater streams cascading down newborn slopes, carrying sand-sized particles of ancient coral reefs toward distant floodplains. Those same particles now form the sandstone of the Bavarian foothills, their rounded edges whispering of journeys that began when dinosaurs still roamed. Glaciers became nature's most ruthless sculptors. During ice ages, rivers of ice up to a kilometer thick gouged U-shaped valleys like the Lauterbrunnen in Switzerland, its sheer walls exposing layer upon layer of folded rock like flipping through the pages of a geological novel. But glaciers didn't just erase, they revealed. When the Aletsch Glacier retreated in the 19th century, it uncovered polished slabs of serpentinite, a greenish rock that once lined the Alpine Ocean's floor. The glacier's slow grind had acted like a lapidary's wheel, polishing these stones to a mirror shine while preserving striations that record the ice's exact flow direction. Wind played its part too. In the Dolomites, towering spires of dolomite rock stand pockmarked by countless holes, not from ancient sea creatures, but from sand blasting by fierce prehistoric winds. These natural sieves trap smaller particles, creating pockets where alpine plants now cling, their roots chemically breaking down the rock even further. Meanwhile, rain became a silent artist. Acidic downpours dissolved limestone cliffs, leaving behind surreal landscapes like the Tsingy de Bimaraha in Madagascar, a razor-sharp forest of stone that mirrors how parts of the Alps might have looked during intense weathering periods. The real detective work happens in riverbeds. The Rhine's gravel banks are littered with pebbles of African granite, carried hundreds of kilometers from their source by rivers that flowed before the Alps fully formed. These exotic stones are time capsules, proving how thoroughly erosion redistributed the collision zone's debris. Even more telling are the layers of sediment in places like the Po Valley, where alternating coarse and fine grains record cycles of mountain uplift and erosion, like a geological metronome keeping time with the Alps' growth. What's astonishing is how erosion aids reconstruction. When scientists find identical fossil assemblages in the Alps and the Carpathians, separated by hundreds of kilometers, it's not proof of migration. It's evidence that rivers once connected these ranges before erosion carved them apart. Similarly, zircon crystals in alpine rivers trace back to long-vanished volcanoes along the ocean's edge, their atomic clocks still ticking from the moment they crystallized. The lesson written in every eroded valley and scattered sediment layer is this: mountains aren't permanent. They're transient features in an endless tug of war between uplift and decay. The Alps lose about a millimeter of height annually to erosion, a rate that seems slow until you realize it means the Matterhorn summit was once 500 meters higher. Yet this very erosion exposes the Alpine Ocean's deepest secrets, turning destruction into revelation, one grain of sand at a time. Picture a Europe unrecognizable today, where the jagged skyline of the Alps dissolves into a coastal paradise of turquoise lagoons and palm-fringed shorelines. This was the world of the Alpine Ocean's heyday, a lush tropical realm where crocodiles basked on muddy riverbanks and the air hummed with the calls of prehistoric birds. Reconstructing these lost landscapes isn't guesswork. It's a forensic art combining cutting-edge technology with clues buried in stone. Start with the fossils, delicate imprints of mangrove leaves preserved in Swiss slate, their veins still visible after 200 million years. Or the petrified trunks of cycads, ancient plants resembling cross between palms and pineapples found near Vienna, their growth rings revealing monsoonal rainfall patterns long vanished from the continent. But fossils alone can't paint the full picture. Enter paleogeographic modeling, where supercomputers crunch data on plate movements, sea levels, and ancient climate proxies to generate shockingly detailed maps. One such simulation shows the Alpine region as a sprawling archipelago, its shallow seas dotted with volcanic islands that belched sulfur into humid skies. The water's edge teemed with life, fossilized trackways in Italian limestone capture the moment a herd of reptile-like creatures scrambled across a tidal flat, their three-toed prints preserved like a prehistoric snapshot. The real magic happens when scientists layer multiple data sources. Drill cores from beneath the Po Valley contain pollen grains from heat-loving ferns, while magnetic minerals in Austrian rocks record the latitude where they formed, close to the equator where the sun blazed overhead. Even the rocks themselves tell stories. Chunks of laterite, a rust-colored soil that only forms in tropical downpours, found today in the Bavarian foothills. Some of the most vivid reconstructions come from unexpected places. In the Dachstein caves, stalagmites hold isotopic signatures of rainfall from the ocean's final millennia, revealing a climate growing increasingly erratic as continents collided. Meanwhile, fossilized insect wings from German quarries suggest dense rainforests where dragonflies with 70-centimeter wingspans darted between towering conifers. The ultimate challenge, visualizing the transitions. As the ocean closed, its coastlines morphed from tranquil beaches into brackish swamps, then into vast river deltas choked with sediment. Computer animations based on seismic data show this transformation in eerie detail. One frame displays a thriving coral reef. The next reveals that same spot buried under 3 kilometers of mountain. Yet for all the high-tech tools, there's still room for old-fashioned detective work. When geologists noticed certain alpine boulders didn't match their surroundings, they traced them back to eroded volcanoes that once peppered the ocean's margins, ghostly landmarks on maps of a world that exists only in stone and memory. What emerges isn't just a postcard from the past, but a reminder of Earth's boundless creativity. The same forces that erased this tropical paradise would later sculpt the Alps from its ruins, proving that every landscape, no matter how permanent it seems, is just a fleeting stage in our planet's never-ending reinvention. Beneath the towering peaks of the Alps, hidden in plain sight, lie witnesses to the Alpine Ocean's demise no bigger than a grain of sand foraminifera. These single-celled creatures, barely visible without a microscope, built intricate shells that now serve as tiny time capsules, preserving secrets of ancient seawater in their calcium carbonate walls. Imagine holding a pinch of alpine limestone between your fingers. Within it, hundreds of these microfossils could tell you the ocean's temperature the day they died, the acidity of the water they swam in, even the season their tiny lives ended. The real magic lies in their chemistry. Each foraminifera shell absorbs trace elements from seawater as it grows, locking them into its structure like a biological hard drive. Scientists use instruments called mass spectrometers to vaporize these shells atom by atom, measuring ratios of oxygen isotopes that act as prehistoric thermometers. Higher levels of oxygen-18, for instance, mean colder waters, while lower levels suggest the balmy conditions of the Alpine Ocean's tropical heyday. Some specimens from the Austrian Alps record surface temperatures of 30 degrees Celsius, evidence that this vanished sea was once as warm as today's Caribbean. But temperature is just the beginning. The same shells contain boron isotopes that track pH levels, revealing how acidic the ocean became during its death throes. In layers corresponding to the ocean's final millennia, boron ratios spike dramatically, painting a picture of waters growing increasingly hostile to shell-building life. This acidity surge matches fossil records showing mass die-offs of larger creatures, proving that the smallest organisms often feel environmental shifts first. Perhaps most astonishing is how these microfossils capture extinction events in miniature. In sediment cores from the Swiss Alps, researchers found foraminifera species that thrived for millions of years suddenly replaced by hardier forms with thicker shells, a clear adaptation to turbulent, sediment-choked waters as the ocean shallowed. Other layers show dwarfing, where successive generations grew smaller and malformed, struggling to build shells in chemically hostile conditions. These changes mirror what scientists observe in modern oceans suffering from acidification, making foraminifera both ancient sentinels and modern canaries in the coal mine. The true power of these microscopic witnesses lies in their ubiquity. Unlike dinosaur bones or coral reefs, foraminifera existed in every corner of the Alpine Ocean, from sunlit surface waters to lightless abyssal plains. Their cumulative fossil record forms a near-continuous timeline, allowing scientists to track changes month by month in some exceptionally preserved layers. In the Dachstein limestone, for example, Alternating light and dark bands in foraminifera-rich strata represent seasonal growth pulses, like tree rings for the ancient sea. What's remarkable is how these tiny timekeepers are rewriting the ocean's story. Traditional models suggested the Alpine Ocean collapsed over millions of years, but foraminifera fossils tell a more nuanced tale. In the Italian Dolomites, a single centimeter of rock contains shells spanning 50,000 years, a time capsule showing sudden swings between warm and cold, oxygen-rich and oxygen-poor conditions. This granular detail reveals the ocean didn't die a slow, steady death, but in fits and starts, with brief recoveries punctuated by catastrophic downturns. The ultimate lesson from these microscopic marvels, that Earth's grandest dramas often leave their clearest fingerprints in the smallest places. A single foraminifera shell weighs less than a snowflake, yet thousands of them, layered over epochs, can tilt continents of scientific understanding. They remind us that in the story of our planet, there are no insignificant characters, only overlooked ones waiting for the right tools and the right eyes to reveal their extraordinary tales. Walk through the Swiss Alps near the town of Glarus, and you'll find something unsettling, a single line in the rock where two eras touch, with millions of years missing in between. This is the Glarus unconformity, one of Earth's most dramatic geological omissions. On one side, 300-million-year-old Permian sandstone sits directly atop 400-million-year-old Devonian limestone, with no trace of the 100 million years that should separate them. It's as if someone ripped entire chapters from a history book and glued the remaining pages together. These gaps, called unconformities, aren't just curiosities. They're forensic evidence of the Alpine Ocean's violent demise. When subduction began consuming the seafloor, entire stretches of crust were lifted above water, exposing them to the elements. Rain, wind, and rivers scoured away layers of rock like sandblasters stripping paint, erasing eons of sediment in what geologists call a great unconformity. The missing rock isn't lost, it's pulverized into the dust that later became the sandstone now resting atop the gap, recycled by the very forces that destroyed it. Some unconformities tell even darker tales. In the Italian Dolomites, a layer of jagged breccia, a rock made of shattered fragments, marks where earthquakes triggered underwater landslides, tearing up the seafloor and leaving chaos in their wake. Above this rubble lies smooth limestone, proof that calm eventually returned, but the intermediate layers gone. This selective erasure reveals moments when the ocean's collapse accelerated. Its death throes so violent they left no record beyond the scars of their passing. The most revealing unconformities hide in plain sight. Along the French-Italian border, a single outcrop shows three separate gaps stacked like geological ghost stories. The lowest marks when the Alpine Ocean first began forming. The middle records its abrupt shallowing. The top coincides with its final disappearance. Together, they form a timeline of catastrophe, each missing layer a silent witness to upheaval. What makes unconformities so valuable is what they force scientists to confront: the limits of our knowledge. In places like the Tauern window of Austria, the gap spans 200 million years, a void longer than the entire age of dinosaurs. Yet within that absence lie clues. The angular edges of surviving rocks show how they were tilted by tectonic forces before being planed flat by erosion. Like a detective reconstructing a crime scene from bullet trajectories, geologists use these angles to calculate the scale of ancient mountain ranges that rose and vanished long before the Alps existed. The cruel irony: these voids often preserve what they destroy. In the Carpathians, an unconformity surface is studded with fossilized worm burrows, tunnels dug into now vanished sediment that hardened into casts before erosion could wipe them away. Elsewhere, patches of iron-rich, hard-ground mark where minerals cemented the seafloor just enough to resist destruction, leaving behind eerie, pitted surfaces that once teemed with clinging shellfish. Perhaps the greatest lesson of unconformities is humility. For all our technology, Earth's history remains fragmentary, full of gaps we may never fill. Yet these very absences push science forward, each missing layer a siren call to dig deeper, question harder, and listen more closely to the stories rocks don't tell. After all, in geology as in life, sometimes what's unsaid speaks loudest of all. Long before scientists pieced together the tectonic drama of the Alpine Ocean, the towering peaks of the Alps whispered their origins through myths passed down by shepherds and storytellers. In the remote valleys of Switzerland, legends speak of a colossal giant named Helvete who once strode across the land, his massive feet carving out lakes and valleys as he battled mountain spirits. To modern ears, this might sound like pure fantasy, but look closer and you'll find uncanny parallels to real geology. Those giants' footsteps, they align eerily with glacial cirques left by Ice Age glaciers. The battling spirits could mirror the earthquakes that still rattle the region as Africa and Europe continue their slow collision. The Dolomites in Italy owe their name to an even stranger tale. Local folklore tells of a mythical kingdom of dwarves who wove moonlight into the mountains, giving the peaks their ethereal glow at dawn and dusk. What's fascinating is how this mirrors the actual composition of the rock. A dolomite stone contains magnesium, which refracts light in a way that makes the mountains appear to shimmer. The dwarves might have been early miners who noticed these luminous qualities while tunneling into the slopes for precious metals. Perhaps the most striking legend comes from the Austrian Alps, where villagers long spoke of a dragon's blood spring, a rust-colored waterfall said to flow from an ancient beast's wound. Today, geologists recognize this as an iron-rich mineral seep, its reddish hue caused by oxidized metals leaching from rocks that were once the Alpine Ocean's floor. The dragon in the story could well be the fiery mantle plumes that fueled the ocean's volcanic demise. These stories aren't just coincidences. They represent humanity's earliest attempts to explain the inexplicable, to make sense of earthquakes that toppled homes or strange rocks that seemed out of place. When Tyrolean farmers found seashell fossils high on mountain slopes, they didn't have plate tectonics to explain them, so they invented tales of great floods sent by gods to punish the wicked. The biblical deluge of Noah, the Greek myth of Deucalion. These stories likely originated from real memories of post-glacial flooding as the last ice age waned. The most poignant connection lies in the Alpine creation wars, myths epics where gods and titans clash, hurling boulders to shape the landscape. Compare this to the actual collision of Africa and Europe, which thrust up not just the Alps but also scattered boulders hundreds of kilometers across Europe. These erratic stones, carried by glaciers during ice ages, became the stuff of legend. In Bavaria, one such boulder was venerated as the throne of a fertility goddess. In Provence, another was said to mark where the devil dropped his luggage. What's remarkable is how these myths encode geological truths in metaphorical language. The Roman belief that earthquakes were caused by Jupiter's chariot wheels rumbling underground isn't so different from our understanding of seismic waves radiating from fault lines. The Norse legend of the world serpent Jörmungandr encircling the Earth mirrors the cyclic nature of plate tectonics, continents splitting apart and crashing together over eons. Even the Alpine tradition of singing stones, rocks that ring when struck, finds a scientific counterpart in the acoustic properties of metamorphic rocks like serpentinite, which chime due to their crystalline structure. These stories do more than entertain. They remind us that science and folklore are two sides of the same coin. both seek patterns in chaos, answers in the unknown. The next time you see an alpine peak silhouetted against the sunset, remember, its true story is no less wondrous than the myths. The only difference is we've traded giants for glaciers and dragon's blood for iron oxides, but the ore remains unchanged. The story of the Alpine Ocean is far from finished, in fact. We're standing on the brink of a new era of discovery, where cutting-edge technologies are peeling back layers of history once thought impossible to access. Imagine autonomous underwater drones gliding through the Mediterranean, mapping submerged remnants of the ancient ocean with sonar so precise it can distinguish between rock types at depths of 3,000 meters. These robotic explorers are already uncovering clues, like a recently discovered seamount off the coast of Corsica that may be a surviving fragment of the Alpine seafloor, its magnetic signature matching rocks in the Swiss Alps. Meanwhile, in laboratories across Europe, artificial intelligence is revolutionizing how we interpret geologic data. Machine learning algorithms can now analyze thousands of rock samples in minutes, spotting subtle mineral patterns invisible to the human eye. One AI system at ETH Zurich recently identified a previously overlooked layer of volcanic ash in alpine sediment, a finding that pinpoints the exact moment a supervolcano erupted during the ocean's collapse, potentially triggering a mass extinction. These digital detectives don't just work faster, they think differently, making connections across disciplines. By cross-referencing fossil databases with climate models, they've reconstructed the Alpine Ocean's currents in stunning detail, revealing how its swirling eddies may have influenced global weather patterns. The next frontier lies beneath our feet, literally. The European Continental Deep Drilling Project plans to bore 12 kilometers into the Alps, extracting cores that could contain pristine sections of the oceanic mantle. These samples might finally answer one of geology's biggest mysteries: why some slabs of the Alpine Ocean's crust sank straight into the mantle, while others got stuck halfway, creating the strange seismic anomalies detected beneath Austria. But perhaps the most thrilling developments come from space. ESA's swarm satellites are mapping Earth's magnetic field with unprecedented precision, detecting faint traces of the Alpine Ocean's subducted slabs. They're cold, dense rock distorting the planet's magnetism in ways that reveal their exact depth and orientation. Combined with quantum gravity sensors that measure density variations from aircraft, we're essentially building a 3D tomograph of the entire Alpine collision zone. Yet for all this technology, some breakthroughs still happen in the field. Paleomagnetists are now using portable superconducting quantum interference devices SQUID to read ancient magnetic signatures in rocks without even collecting samples. In the Italian Apennines, this revealed a startling twist. Sections of the ocean floor rotated 90 degrees during collision, like ships caught in a whirlpool. The coming decades promise even wilder possibilities. Nanoscale sensors could one day be injected into rock fractures to monitor tectonic stress in real time, while neutrino detectors might image subducted slabs by tracking how these ghostly particles change as they pass through Earth. Some researchers speculate we could eventually simulate the entire Alpine Ocean's life cycle in a quantum computer, atom by atom. What makes this moment so extraordinary isn't just the technology, it's the questions we're finally equipped to ask. Did microbial life survive in the ocean's subducted crust? Could residual fluids from its demise still lubricate earthquakes beneath the Po Valley? Every answer rewrites not just the Alpine Ocean story, but our understanding of how oceans live, die, and rebirth themselves across our planet's history. The rocks have kept their secrets for 200 million years now. At last, we're learning how to listen. Imagine strapping into a virtual time machine, where a few clicks transport you 250 million years back to hover above the Alpine Ocean as it sprawls across prehistoric Europe. Digital reconstructions have revolutionized how we visualize this vanished world, not as static illustrations, but as dynamic, interactive landscapes where you can zoom from continental scale down to individual reefs teeming with virtual ammonites. The University of Lausanne's Paleo Atlas project lets users toggle between tectonic plates like layers on a smartphone map, watching Africa inch toward Europe at variable speeds. Speed up the timeline and the ocean basin shrinks like a deflating balloon, its coastlines retreating in jagged increments as virtual sediment fills the shallows. These tools don't just show change, they make you feel it. The magic lies in the data behind these simulations. By feeding satellite altimetry, seismic surveys, and fossil distributions into gaming engines, scientists create landscapes where every mountain and river follows real geological constraints. Switzerland's Fleischzoom app overlays modern alpine topography with translucent layers of ancient shorelines, revealing how today's hiking trails trace paths once walked by crocodilians. Tilt your device and the view shifts to cross-sections exposing subducted slabs, ghostly blue shadows representing the ocean's lost crust still embedded deep beneath the Matterhorn. What's transformative isn't just the visuals, but how they reshape scientific inquiry. When geologists noticed their digital Alps lacked a crucial sediment layer, they realized their models had underestimated the ocean's western extent. Subsequent drilling in Spain confirmed the oversight, a breakthrough sparked by a pixelated anomaly. Similarly, paleoclimatic maps that animate monsoon shifts over the ocean's lifespan have upended theories about why certain fossils cluster in unexpected regions. Seeing evaporation patterns swirl over digital seaways makes it obvious how currents carried heat and life along forgotten pathways. For educators, these tools are game changers. Students can now dive into the Alpine Ocean's depths using VR headsets, collecting virtual rock samples that reveal their real-world compositions when examined. The Tectonic Explorer program from Harvard lets users tweak collision angles and watch how the Alps deform in response, a hands-on lesson in cause and effect that once required abstract equations. Even museums are adapting. Vienna's Natural History Museum replaced static dioramas with touchscreens where visitors can erode a mountain range with finger swipes, exposing the ocean's fossils hidden inside. The most profound impact might be temporal. Traditional geologic maps compress time into flat colors, but interactive versions let you scrub through millennia like a video timeline. Watch the Julian Alps region transform from open ocean to volcanic archipelago to coastal swamp, all while a counter tracks the years in millions. This temporal literacy helps even novices grasp scales impossible to convey in textbooks. When you witness the ocean's 200 million year lifespan condensed into 90 seconds, its demise feels less like theory and more like destiny written in land and water. Yet these reconstructions aren't infallible. Disagreements flare over details like water depth estimates or the exact hue of Triassic skies. Some models render the ocean as a vibrant turquoise based on carbonate chemistry, while others opt for greener tones accounting for prehistoric phytoplankton blooms. These debates aren't cosmetic, they reflect fundamental questions about the ocean's ecology and light penetration. The beauty of digital tools is their flexibility. When a new fossil discovery suggests warmer temperatures in the Western Basin, the entire model can be adjusted in real time. What emerges from these pixelated worlds is something textbooks could never deliver, the visceral sense of Earth as a living, breathing entity. When you watch the Alpine Ocean vanish beneath your cursor, its waters squeezed out like juice from tectonic fruit. You don't just understand subduction, you witness it. And that changes everything. Suddenly, the abstract becomes tangible, the ancient feels immediate, and the Alps themselves transform from static monuments into characters in the greatest story ever told, a tale written not in ink but in stone and time. Could the Alpine Ocean ever return? It's a question that seems straight out of science fiction, but the answer lies in Earth's relentless cycle of tectonic rebirth. The process that erased this ancient sea, subduction, is the same force that could one day recreate it, though not in our lifetime or even in the lifespan of our species. Right now, Africa is still inching toward Europe at about the same speed your fingernails grow, squeezing the Mediterranean Sea in a slow-motion vise. Geologists predict that in roughly 50 million years, this shrinking sea could close entirely, potentially forming a new mountain range where the Alps stand today. But here's the twist: if the tectonic dance reverses and these continents begin to pull apart again, the cracks between them could fill with water, birthing a brand new ocean. We've seen it happen before. The Atlantic Ocean was once just a rift valley in the supercontinent Pangaea, much like East Africa's Great Rift Valley today. So while the Alpine Ocean itself is gone forever, its story reminds us that Earth's geography is never permanent, just waiting for the next act in a planetary drama spanning hundreds of millions of years. Now let's tackle another head-scratcher. How do mountains melt? It's not like watching ice cream drip on a sunny day. When geologists say mountains melt, they're talking about rocks deep underground transforming under extreme heat and pressure. Picture a slab of the Alpine Ocean's crust being dragged dozens of kilometers beneath Europe during the collision. Down there, temperatures soar past 500 degrees Celsius, and minerals that were stable near the surface begin to break down. Water trapped in the rocks acts like a flux, lowering their melting point until they literally turn to slush, a process called partial melting. The resulting magma can bubble upward, fueling volcanoes or crystallizing into granite plutons that form the cores of new mountains. Sometimes the rocks don't fully melt but morph into entirely new minerals, like the dazzling blue glaucophane in blueschist rocks. These transformations aren't just academic curiosities. They're the reason the Alps contain such a chaotic jumble of rock types, from ocean floor basalt to high-pressure eclogite, all baked together in Earth's subterranean oven. Another burning question: why do we find marine fossils high in the Alps? The answer is written in the rocks like a geological lift receipt. When the Alpine Ocean closed, the sediments that had accumulated on its floor shells, coral reefs, even microscopic plankton, were caught in the collision like crumbs between two slices of bread in a sandwich. As the continents squeezed together, these layers weren't just pushed upward, they were folded, fractured, and sometimes even flipped entirely upside down. In the Glarus Alps of Switzerland, you can see fossilized ripple marks from an ancient seabed now perched vertically on a mountain face, as if someone took a snapshot of the ocean floor and stood it on its edge. The fossils didn't climb there, the earth moved beneath them, carrying these sea creatures' remains to elevations they never could have reached in life. It's one of the most visceral reminders that the ground beneath our feet is anything but static. One mystery that stumps even experts: why are some parts of the Alpine Ocean's crust missing? Subduction usually recycles oceanic plates back into the mantle, but occasionally, slices get scraped off and preserved on land as ophiolites. The Alps have plenty of these, yet there are glaring gaps where geologists expect to find more. The leading theory involves microcontinents, small landmasses that may have existed within the ocean, acting like bulldozer blades during collision, shearing off some crust while allowing other sections to vanish into the depths. Recent seismic imaging beneath the Po Valley hints at lost fragments of this crust still lodged in Earth's mantle. Their cold, dense rock distorting gravity, measurements like ghosts haunting the collision zone. Finally, let's address a question that bridges past and present. Could the Alpine Ocean's collapse teach us about climate change today? Absolutely. The ocean's sediments record periods of abrupt global warming when underwater methane deposits destabilized, releasing greenhouse gases that spike temperatures. Sound familiar? There's also evidence that as the ocean shallowed, its weakened currents failed to distribute heat effectively, causing regional climate chaos. These ancient lessons underscore a crucial truth: Earth systems are interconnected in ways we're only beginning to understand. When we alter one piece of the puzzle, whether through natural forces or human activity, the ripple effects can be far more dramatic and lasting than we ever imagined. The collapse of the Alpine Ocean wasn't just a footnote in Earth's history. It was a tectonic symphony that reshaped the planet in ways we're still deciphering. Every ripple in the Alps, every fossil trapped in limestone, every seismic tremor beneath Europe whispers fragments of this epic tale. But what makes this story truly extraordinary isn't just its scale or drama, it's how intimately it connects to our world today. The same forces that swallowed an ocean now fuel the geothermal springs of Budapest, and the same mineral veins forged during the collision today yield the gold and copper in our smartphones. This vanished sea teaches us that change is the only constant. Continents drift, mountains rise and crumble, and even the mightiest oceans can vanish into the Earth's depths. Yet in that impermanence lies a profound resilience. The Alpine Ocean's demise birthed the Alps, which in turn became cradles for civilizations, engines of weather patterns, and archives of climate history. Its legacy lives on in the vineyards of Piedmont, where grapes thrive in soils enriched by ancient seafloor sediments, and in the snowpack of the Brenner Pass, whose meltwater carries traces of minerals from the ocean's hydrothermal vents. For scientists, the Alpine Ocean is more than a case study. It's a Rosetta Stone for understanding planetary evolution. The techniques honed here, from decoding microscopic fossils to modeling subduction zones, are now used to predict earthquakes from California to Japan. And the questions this ancient sea inspires about climate tipping points, biodiversity collapse, and continental formation are the very ones shaping our future. As we stand on the shoulders of this geological giant, we're reminded that Earth's story is endlessly layered. The next chapter might be written in the rocks of the Himalayas, where a new ocean is forming in the Tibetan Rift, or beneath Iceland, where the Atlantic's birth mirrors the Alpine Ocean's early days. One thing's certain: the same patient, powerful forces that orchestrated this epic collapse are still at work, knitting and unknitting the fabric of our world. So the next time you see a mountain peak or skip a stone across a lake, remember, you're not just touching the present, you're brushing against deep time itself, where oceans rise and fall, continents collide and part, and every landscape holds secrets waiting to be unearthed. The Alpine Ocean may be gone, but its story is far from over. It pulses in every earthquake, lingers in every alpine breeze, and invites us to keep exploring, one layer at a time.